Hello, this is a presentation on the Weave SDK. Today we will attempt to give you a nice overview of the architecture of Weave SDK, explain what it's used for, and give you insights in how to build your own application. This will be a series of videos covering various aspects of the Weave SDK, and you can follow up with documentation and online tutorials if you're interested in these videos for more details. First of all, what is Weave? Short, Weave is a framework to build blockchains, much like Django is a framework to build web applications. It relies on the Tendermint consensus engine to do the networking and the block production to run a Byzantine fault-tolerant consensus algorithm. What Weave does is it fills the ABCI interface for state machines, in much the same way that Django returns a WSGI interface to talk to Apache handling the file serving, networking, WebSocket requests, etc., and Django just handling the logic to process, not the networking and authentication, networking and load balancing, other various levels in front of the application. Tendermint does that here, and the ABCI interface allows a state machine to plug into the blockchain. Weave implements the ABCI interface and is thus a state machine, a deterministic state machine. If these are not familiar concepts for you, I suggest you look at the Tendermint documentation or our brief overview on docs.iov.1, where we discuss this as well. What Weave guides you is it provides you a lot of flexibility how to construct your application, from choice of which database to use, to how to build a middleware stack to process transactions, to implement your own handlers, to implement your own parsing logic, serialization logic, anything else you want. So it provides you quite a bit of flexibility using a variety of well-defined interfaces as the core of the architecture, the framework, allow with some concrete implementations that we provide, but you can also swap them out with your own. We provide a lot of standard components you can pick and choose from. These include very basic things such as signature verification, and more complex things like multi-state contracts or governance voting. We also, every single item can be swapped out. So you can use a different signature algorithm or use none at all if you don't want to use signatures. I mean, it doesn't make much sense, but you can do anything you want there. You also don't have to use tokens if you don't like tokens. For example, a proof of existence blockchain, a centralized permission blockchain, private blockchain, this wants to record data as a data log, can have signed entries but not need tokens. We will dive into the architecture of Weave and a few select components in this video series. There will be a whole series here, and there's more information available at docs.iov.1. The entire source code is available on GitHub under iov.1/weave. I suggest you take a look at it. It's quite mature. We are at version 0.20 now, and we are nearing release of our first production blockchain built on the Weave framework. It is undergoing audits, security audits, and is, as of end of July 2019, is nearing production readiness, and I think is compatible for anyone to start building apps on top of it. So to explain a bit of the overview of what we work with here, when we fulfill the ABCI interface, we mainly handle transactions. The interface there mainly handles the lifetime of transactions, processing transactions. It's a state machine, so what it does, it takes a transaction to drive changes of state, and then it processes them to change the state. There are two types of messages we have. The first one's a check TX, which basically says it's a filter message. It looks at the current cached state, it makes a scratchpad state, and will execute your this transaction in some sort of isolated state to see whether or not it will be valid. This is used as a quick filter for the mempool, so it can reject transactions that are not valid. So if the signature is invalid, if the account has no money in it, etc., if it cannot pay the fees, it should be immediately rejected. We should not add it to the block. We should just drop it off. We should not propagate it. Once it's made into a block, we run it again. Note that it may error still, even after including a block. We want to limit, the checktx idea is to limit the number of transactions that are included in a block but will fail later on. But we don't want to spend too much time on checktx either, because then it will become a bottleneck. Normally what happens, the entire time checktx keeps coming in, every time a transaction comes in, it may be executed any time. When a consensus is reached upon a block, the finalized block is then sent to the state machine in a series of events. First, begin block, saying a new block was formed. This includes the new header information, including timestamp and height, along with the valid information who signed it. Then deliver checks is called once for every transaction included in a block. This may be called 0 times, may be called 1,000 times, depending how big the block is. Deliver TX will process each transaction in order. They must be in the same order all the time, deterministic results between all nodes, and it will return a result. It can return an error signifying this transaction failed, or a result saying it succeeded and possibly turn some data back. If it succeeds, it should definitely update the state. End block is called after all delivered transactions have been called. This is a place where the ABCI application can return information back to Tendermint to ask it to update the validator set or to update consensus parameters, such as timings and maximum block size and minimum gas fees and various things like this, which are enforced by Tendermint. So all this information can be passed in, returned to end block. And after this is done, and Tendermint is happy with it, commit is sent, and that basically holds a lock, so no other messages are sent during commit. And this will write the state to disk. So the ABCI app now has to flush all that current state is created during processing the block, is all basically one open transaction. And then it writes it to disk, syncs to disk, and then it can do any other state changes that need a lock, such as updating the checktx cache state, or any other internal bookkeeping it needs. Once the commit is finished, then other transactions like checktx and query will come in again. This is the lifetime. Checktx will flow all the time, and the sequence of begin block, end deliver tx, end block, commit block will happen every few seconds as blocks are forged. There are a few other calls the ABCI interface exposes. The two important ones there are query. Query is important, so the state is only stored in the application, never in Tendermint. And if the client user wants to see something like the balance of their account, they should be able to query for that. Tendermint handles the query and basically passes it on more or less verbatim after some validation to the ABCI application, which then will return information or no information or an error if it's malformed. This returns a view of the state of the current height. It also has an option to look at recently previous blocks. So usually we store maybe 20 or 100 recent blocks, and you can query that, which allows you to make multiple queries at the same height to get a consistent viewpoint. For example, if I want to query your balance and my balance, I might want to query them both, two different queries at the same height, because if we're sending money back and forth, the sum of balances between our accounts would be 100, but if I query mine at one height and yours at another height, the sum might be 105 or 90, depending on if there are transactions in flux. So it allows querying a specific height, which is a very important point to implement. There's also another call called info, which returns some basic information like the current last block height, last block hash, maybe it's a little app text. And this is basically used for handshaking. When it starts up, the application talks to Tendermint and says, hey, what's the last block you processed? What hash did you have? Tendermint looks it up and says, okay, I have that same one too, and I have 5 blocks that you've not processed yet. I start with these, and then I continue syncing up. This is very important for syncing. On top of this interface, we provide basically a base app. The base application implements the ABCI interface, but abstracts it for us. So then it provides us access to Weave internal interfaces. We don't have to use those same types. We then basically create our own abstraction inside of that. ABCI provides a very consistent wire level protocol, but that same wire level protocol does not need to be passed in. The same way that an HTTP post is a few lines of text with a space and then the body of the thing, which is basically a text object, that is parsed and turned into a map of headers, a path which is parsed out of the first line, gets a method parsed out of the first line, get slash HTTP 2.0, and the body then is a stream that you can parse a JSON object. And all of that parsing is usually done in web applications. They don't show you just the raw text that was posted. They parse out the headers, they parse out they parse the body into a JSON object, and they give you the path as a separate object in the request. The same way, we don't want to show the raw ABCI details. We basically parse those out into something that we find more usable in our application to allow us to work with Go structures in memory. The main pieces that you're allowed to customize is when you create a BAS application, it takes a data store, which is basically a store which can be committed to disk, and it knows how to wrap itself as a KV store, key value store, and we'll look into that more detailed. This data store must be Merkleized, meaning it be able to produce a Merkle root. We'll go into that more detail in later sections about proofs, but the point is you have to quickly produce a hash which is unique to the data. So if two nodes have different data, even one byte is different, they should have different hashes. The Merkle trees allow you to quickly compute that. So the data store must be Merkleized, and we use key value stores here. And as a Merkleized tree, it can produce proofs later for individual, for light proofs for clients. We pass initializers in, which are called on init chain. The first time that the blockchain starts, it calls a init chain. It passes the Genesis file in, so we can parse out different fields in the Genesis file to create the initial state of the blockchain. That's very important. We don't have the same code running, but the token distribution and certain permissions or settings may be different, which create wildly different blockchains. So we create initializers. You pass that into the base app, how you initialize, how you process that Genesis file, a TX decoder, which is run on check TX and deliver TX to parse out the transactions. Tendermint considers them just a raw byte slice. We actually need to decode them into a Go struct, and the TX decoder logic is app dependent logic, which handles that. The handler basically is what handles the transaction. Once you decode it, a handler is the one that processes the transaction and will return a result or an error. We'll go into that much more in detail. It's a very fundamental portion of this. A ticker is a callback called every begin block, which allows you to produce, to run repeated jobs every time. It may also run cron jobs, for example. Run this block height 500, run this transaction, or it may check every block for certain things. As is done in Cosmos SDK, they update the validator state every, I think, end block actually. Our tickers run begin block. And the query router, which handles all the query calls coming in. So this can basically, you can query with different path and data, and this will then route that to different query handlers that then will handle the particular queries. By implementing these interfaces, a Merkleized data store, an initializer to handle init block, a TX decoder and handler, which will process all check TX, deliver TX, ticker to allow repeated tasks called a begin TX, and query router for queries. With these interfaces, we basically have nice high-level Golang interfaces we are familiar with, and the rest of the binding to the whole lifecycle from the ABCI app is handled by base app. It is not too much. It is kind of opinionated. It's not very opinionated. It is just basic bookkeeping stuff that we need to do anyway, so it just handles all those details for us. Another main point about Weave is it breaks into modules. So while base app adapts this into interfaces, we get these giant high-level interfaces like initializer, handler. we don't want to implement one giant handler to have all the logic of the blockchain. Instead, we have the idea that we break them into modular units for easier reuse. If you look at the source code, there's an X directory with maybe 10 or 15 different subdirectories in it. Each one of those are extensions or modules, as you want to call them. And these provide basic components as signature validation, your token balances, checkpointing, batch messages, as well as complex things, multi-sig, atomic swap, governance elections, distribution, contracts, etc., etc. All of this information are considered modules and extensions. You can combine them together. And we have a number of helper functions which will combine many handlers together into a router. It will stack up decorators to create a handler. It will chain a bunch of initializers. It will connect a bunch of router query handlers. So we basically want to produce a lot of relatively independent modules which can run independently. And when building an application, you just basically chain a bunch of those together into one handler, which you pass into base app. And however you create that handler, whether there's one handler you write or whether you use giant router constructs for that, it will just handle that. So remember, everything is optional. It can be swapped out. Usually it doesn't break other modules. With their dependencies on modules, you try to keep interfaces they're passing the constructor rather than hard coding modules. Even the cache module which handles token balances is used by many other modules to move balances around, and that is passed in as an interface. So if you want to change the token module, you can pass in a different implementation of that. That is the whole design. It's completely modular. Okay, so that was that. I will produce another video on transaction flow, and I will get to that later.